All right, this is section 4.1 on quadratic functions. So in this chapter, we will explore quadratic functions and also polynomial functions. And we're going to continue on with what we did in Chapter 3. In Chapter 3, we studied linear programming, where linear programming allowed us to optimize a problem when we could express that problem as an objective function, a linear objective function, and a system of linear constraints. Okay, in that situation, we could find the optimum solution, either the point that minimized or maximized the objective function. Okay, in this section, section 4.1 on quadratic functions, we're going to continue with that same theme of optimization. And what we're going to see is that often functions that we use often in business, like revenue and profit, will often be a quadratic function. And we can, there's a simple way to optimize to find the maximum or minimum of a quadratic function, and that's what we're going to cover today. Okay, so the definitions. The standard or general form of a quadratic is f of x equals ax squared plus bx plus c, where the sign of the coefficient a, that coefficient on the leading term of the quadratic function, the sign of the coefficient a determines whether the quadratic opens upward, that's when a is positive, or downward, that's when a is negative, as shown below. Okay, and you will often see quadratics written in the form f of x equals a times quantity x minus h squared plus k. This is called vertex form. We'll see more about vertex form next. Okay, so you see in the pictures there, they're a little fuzzy, but there's different points on each parabola. The graph of a quadratic function is a parabola, and it has this kind of U shape. And it will either open upwards when a is positive or downwards when a is negative. Okay, and we have intercepts, and we'll define all this terminology below. Okay, so the vertex of a quadratic is either the lowest or highest point on the graph of the quadratic. So either the top of the hill or the bottom of the valley. If a is greater than 0, the vertex is the lowest point, while if a is less than 0, the vertex is the highest point. Okay, and when written in vertex form, this f of x is equal to a times quantity x minus h squared plus k, the coordinates h comma k identify the vertex of the quadratic. Okay, so in this little box here, we have a formula that gives you a way of determining the vertex of a quadratic function when it's given to you in standard form or general form, okay, when that ax squared plus bx plus c form. All you need to know is b and a. If you know b and a, then this h, the h part of the vertex from this hk pair, so h is the x value, the x coordinate of the vertex, and k is the y coordinate of the vertex. And h is going to have the value of negative b over 2a. Okay. Now, where does that negative b over 2a come from? I'm not going to go into that in this section, but your book does have a discussion of that if you're interested. Okay, and then how do we get k? Well, the simplest way perhaps is to just evaluate your quadratic function at h. Okay, why is that? Well, if you look here, you'll see if we write the function in this vertex form and we evaluate it at h, then what do we get? We get f of h is equal to a times quantity h minus h squared which is just 0 squared, plus k. And of course, we just get a times 0 plus k, which is k. So, yeah, so when the point is that when you write a quadratic function in this special vertex form, those quantities h and k correspond with the vertex of the quadratic. So either the lowest point or the highest point, depending on the sign of the lead coefficient a. Okay. We also have the concept of intercepts. These are displayed on the graphs here. The intercepts of a quadratic are where the graph crosses the x-axis or the y-axis and have the ordered pairs. So x-intercepts will always have ordered pairs like this, where the x value is some number and the y-coordinate will always be 0 because these are points on the x-axis. And the y, notice there can be multiple x-intercepts. There could be 0, 1, or 2 x-intercepts for a quadratic function. But a quadratic function will always have just one y-intercept, okay? And the y-intercept will always be of the form 0, comma, some number, like c here, okay? So why always of that form? Well, because every single point on the y-axis has an x-coordinate of 0, okay? Okay, the domain of a quadratic function is always negative infinity to positive infinity. And so there's no restrictions on the domain of a quadratic function. The range of a quadratic function, though, however, is not going to be all real numbers. It's going to be, from negative infinity up to some point. That's if you have a parabola that opens downward, right? Or from some point upwards. So from some k to positive infinity if you have a parabola that opens upwards. Okay. Let's move on to the first exercise. Consider the graph of the quadratic f of x equals negative x squared plus 6x minus 5. Okay, so this is just a little warm-up exercise to get us used to some of the terminology associated with quadratic functions and functions in general. So what is the value of f of 2, or f evaluated at 2? Well, I could plug it into the function there, which they give us, but we have a graph here, and we can see that here's the point 2 on the x-axis, so this is the x-axis. When x equals 2, that's associated to this. This is the point on the graph, and that means that point has y-coordinate of 3, it looks like to me. So f of 2 equals 3. Let's see. Let's check it with the actual the function given to us as an expression. Let's see. Negative 2 squared would be negative 4 plus 6 times 2 is 12 minus 5. So that would be negative 9 plus 12. Yeah. 12 minus 9 is 3. Okay. B. Let me fix that. That's an F. The vertex of the quadratic is at pair what? Well, the vertex is this point up here. And let's see, that would have coordinates of 3, 4. The y-intercept is at the ordered pair. So here's the y-intercept. And a y-intercept always has an x-coordinate of 0, but the y-coordinate here is negative 5. The two values of x that make f of x equal to 0 are, well, we can look at the graph here. That's these 2 points. The 2 points that intercept the x-axis are where the function is 0. Okay, the x-intercepts. And these occur at x equals, let's see, 1 and 5. So I'll write it this way, x equals 1 or 5. Okay, moving along. The graph the quadratic f of x equals x squared minus 8x plus 12 and identify the following. Okay, well, what I'm going to do is actually go through all the steps here and then, well, steps A and B at least, and then graph the function. So let's see, because finding the x-intercepts, the y-intercept, and the vertex is really helpful when graphing a quadratic function. Those are the 4 things you want to always find: the x-intercepts, y-intercept, and the vertex. I guess that's 3 things. Depends on how many x-intercepts you have, right? Okay, so the x-intercepts. This is where f of x equals 0, so I want to set x squared minus 8x plus 12 equal to 0, and I want to solve this equation. I'm going to try to factor this, and I get, let's see, I need 2 numbers which multiply to 12 and sum to 8, 2, and 6, right? Let's see here. Yeah, that'll work because negative 2 times negative 6 is positive 12, and then negative 2x and negative 6x gives me negative 8x. Okay, and so then the 2 x-intercepts are at x equals 2 and 6. Okay, let's plot those on the x-axis, 2 and 6. So the graph will cross the x-axis at those 2 points. Okay, let's see. The vertex is at, and now this is, you just need to memorize this h, this formula for h. H is equal to negative b over 2a. Okay, where a is the coefficient of the quadratic term, b is the coefficient of the linear term, and we don't need it in this formula, so we have a, b, and c here. C is the constant term of the quadratic function. Okay, so let's see. B is negative 8, so negative 8 is positive 8. And 2a, a is 1. There's an implied coefficient of 1 there, so 2 times 1 would be 2, so this is at 4. Okay, and how do we get k? This is also, you just need to kind of memorize this. K is equal to the function, the quadratic function, evaluated at h. So this is going to be f of 4, which is going to be 4 squared minus 8 times 4 plus 12. What does that simplify to? I get 16 minus 32 plus 12. I'm going to add the 2 positive terms together. I get 16 plus 12 is 28. And then I have negative 32 plus 28. That's going to be negative 4. Okay, so the vertex is at the point 4 comma negative 4. Okay, so 4 comma negative 4, that would be this point here on the graph. While we're at it, what about the y-intercept? To get the y-intercept, you evaluate the function at x equals 0. And when I put in 0 into this function, the quadratic term gives me nothing. The linear term gives me nothing. It's just the constant term, which is 12. But I don't have, my y-axis doesn't go up to 12 on this graph, so the y-intercept doesn't really help me in this case. So let's see if I can get a reasonable sketch of this quadratic function. I want to get something. Whoa, it's a little hard to write at this angle. Maybe something like that, and oops, something like that. I'm not much of an artist there, but that'll work. Okay, how about parts C through F? This is one of those problems with, let's see, 6 parts, huh? Oh no, 7 parts. No. we ran out of number. We should call this G, I suppose, but okay. F of x is increasing on the interval what? Looks to me like from 4 to infinity, positive infinity, and we always use open intervals for this type of stuff. And the function is decreasing, meaning that the function values are getting smaller as x increases. So the function is decreasing from negative infinity to the vertex, which occurs at x equals 4. And f of x has a maximum or minimum at x equals 4. Give the domain of f of x. Well, for all quadratic functions, the domain is all real numbers. Give the range of f of x. Let's see. So this would be from -4 all the way up to positive infinity. Okay, and to get the range, I'm just projecting points onto the y-axis. The graph will project on all values of the y-axis above -4. Okay, next exercise. Let's see. A company's profits when it sells X thousand items is predicted by the model P of x equals -3x squared plus 1,530x minus 15,000. Okay, so we're talking about profits here, and x is in thousands of items. And what else do we know? The lead coefficient of our quadratic function is negative. It's -3. So this is the graph of this function will be a parabola that opens downwards. Okay. So what is the company's startup cost or fixed cost? Well, this is how much it costs before you even begin producing the very first item. When you've produced 0 items, how much money have you spent already? So this is going to correspond with P of 0, the profit upon producing and selling 0 items. And this is going to be -15,000. Right? Clearly, when I put in 0 for x, I just get -15,000 out of that function. So my startup cost is, it looks like this is, it doesn't say specifically it's in dollars, but I'll just assume dollars here. Looks like $15,000 in startup cost. Okay, part B. How many items will the company need to sell to break even? So notice this is very similar, but just subtly different. Breaking even is when your profit equals 0, not when your items, the number of items made and sold is 0, but the profit is 0. So we want to set not x equal to 0, but y. So we want to set the output of the function equal to 0. In other words, we want to solve this equation, negative 3x squared plus 1530x minus 15,000 equals 0. Okay, so I have a quadratic function, or sorry, a quadratic equation now. I have 0 on the right-hand side. I want to factor this. But before I begin the reverse of FOIL, I noticed that every single coefficient in this function has a factor of 3 in it. And heck, I might as well just get rid of, I'm going to divide both sides of this equation by negative 3. Okay, and let's see here. So when I divide every quantity on the left-hand side by negative 3, I'm going to get x squared, so positive x squared. And then here, I'm going to get, let's see, I'm going to use the calculator to do this. Why tax my mind that much? I'm going to do 1530 divided by 3. That's 510. Okay. So this is going to be minus 510x. And then plus, I'm going to divide negative 15,000 by negative 3, and I'm going to get 5,000. Okay, so the point of doing that is I get a slightly simpler equation to solve. And I prefer to have a coefficient of 1 on the quadratic term if at all possible, because FOIL is easier to do, or the reverse of FOIL, I should say. Okay, I need to find two numbers which multiply to 5,000 and sum to 510. How about 510? Yeah. So I'll write it like this. And there we go. Yeah, that gives me positive 5,000 and negative 510. So the answers are x equals 10 or 500. Okay. But remember, really, we're measuring x in thousands of items. So, in other words, the quantity, because x is in thousands of items, so the quantity that all of these x values correspond with is we got to multiply everything by 1,000. So the quantity I really need to sell to break even is going to be 10 times 1,000. So Q is equal to 10,000. So I need to sell 10,000 items before we break even. Okay. Notice if I sell 500 times 1,000, 500,000 products, I will break even as well. But that's because, well, the graph of this function is going to look something like this. And we're going to have these two break-even points, right? Where this is x and this is p of x. It's a quadratic that opens downward, okay? Now, the next question, part C, is about how do we get the vertex of the parabola? How many items should the company sell to maximize profits? Well, here you just have to remember the formula for h and k. So h is equal to negative b over 2a, which in this case is, let's see, here's my a, here's my b, and here's my c, right? So negative b is going to be negative 1530, negative 1530 over 2 times negative 3, which is negative 6. I'll use the calculator for that. $15.30 divided by 6, $2.55. Okay, so remember, it's really 1,000. I've got to sell 255,000 items in order to maximize my profits. Okay, so again, Q is going to be 1,000 times this quantity of 255. So this is 255,000 items is what I need to sell to maximize profits. Okay, what will my profit be? This problem doesn't, no, we're done at this point. But what will my profit be? Remember, you evaluate the function at this h value. So, but we want to this is h, okay? This 255 is our h. So we want to plug that into the function, into the original function of negative 3x squared plus 1530x minus 15,000. So that would be so negative 3 times 255 squared plus 1530 times 255 minus 15,000. I think I'll pull up the calculator for that. Let's see, and we'll do negative 3 times 255 squared plus 1530 times 255 minus 15,000. So it looks like, again, we'll assume dollars here. It didn't specifically say, but $180,075 in profit, okay, if we produce 255,000 items. Okay. And this concludes part 1 of section 4.1.